Bismillahirrahmanirrahim. In this video, we are going to continue with our topic that we started last week, and that is normalization. Here we will look at the next advanced normal forms. So we have done with the first three normal forms, and we are going to look at three new normal forms, and we'll see that there are some problems that were still remaining even after we have completed the first three normal forms. So we'll look at what kind of problems are remaining and how to deal with that. And in the next lecture, we'll look at some examples of which we encounter in the real world, where we'll see the problem and then we'll find the solution to that, and we'll propose the new decomposed versions of the table. So just to recall, we have studied the first three normal forms, and the first normal form, the basic data is the unnormalized data. In the unnormalized data, there is possibility of repeating groups, repeating attributes or values in that attribute, and there can be multi-values in an attribute as well. So multi-valued attributes and repeating groups, these can be part of the unnormalized form. But if you remove that and you can replicate it into new rows, or you can divide the table so that there are no repeating attributes, then such a schema is in the first normal form. And when we say the schema is in a first normal form, it means every single table in that schema will have this attribute. We have this constraint attached to it. So no table in the entire schema, the schema is a collection of tables dealing with some properties. So if you're dealing with the school management system, so all the tables that are related to that school management system combined will form the schema or the database design. So when we say that the schema or the design is in the first normal form, it means that every single table that belongs to that schema must conform to the rules of the first normal form. So when you remove the multi-valued attributes and you remove the repeating groups, you arrive at the first normal form. However, the first normal form, we saw that it has also its own problems, problem with insertion, problem with deletion, problem with updation, and there could possibly be inconsistency if you update one part and you fail to update the other part. So you can have two versions of the same truth in your database. So to deal with that, we go to the second normal form, and to go to the second normal form, you first have to be in the first normal form, and in addition to that, you are going to remove partial dependency. So a non-key attribute depending on a part of the primary key, that's a problem. If you can remove that, then you are in the second normal form. And once you have attained the second normal form, in addition to that, if you remove the transitive dependency, that is A depends on B and B depends on C, then you are in the third normal form. So once we have done with the third normal form, in most cases this is sufficient. However, there are going to be cases where there is a candidate key dependency. We'll look at what is a candidate key, and we have studied it, but we'll just look at it in the next slide as well. And then we have other problems related to multi-attribute dependency, and there are other dependencies as well, which will form the fifth normal form. So let's look at the definition of a prime and a non-prime attribute. So a prime attribute is an attribute set that belongs to any candidate key. These are called prime attributes. What's a candidate key? A candidate key is something that could have been a primary key. So all the possibilities that will give you unique values, they are candidate keys, and among those candidate keys, you select one of them and make it the primary key, and the other ones are alternate keys. They could have been a primary key, but they're not, but they're still part of the candidate key. So any attribute that is part of any candidate key is a prime attribute, and an attribute that is not part of any candidate key, that is called a non-prime attribute. So this is important to figure out which are the determinants and which are the attributes that are determined. So which are the ones we depend on and which are the ones that actually depend. So non-prime attributes are also called as non-key attributes. For instance, if you have this example, so you have the social security number, you have the name, you have the age, you have the city, and you have the phone number. So the ID, every individual will have a unique ID. Since it is unique, it's potentially a primary key, so it's part of a candidate key, and therefore SSN is a prime attribute. Name is not unique, so it's not going to be part of a primary key, so it's not a candidate key, and therefore the attribute name is a non-prime attribute. Age is the same as name, and it's also a non-prime attribute. City and phone number are also non-prime attributes. So the reason phone number is a non-prime attribute is that one person can have multiple phone numbers. So for that reason, you cannot have it as a candidate key. Besides, if you have a social security number, you don't need anything else to do to form uniqueness. Social security number itself is unique. So all I need to do is somewhere here I need to underline this just to show that this is my primary key, and then therefore this is a prime attribute, and all the rest are non-prime attributes. So with this knowledge, let's move on to the problems we can face and how to deal with them and which normal form it is. So the first one that comes to mind is the BoyceCodd normal form. It's also sometimes called as 3.5 NF because it's very close to the 3 NF with just one stricter constraint, and it's a slightly stronger version of the third normal form. And what happens is that if a relational schema is in the BoyceCodd normal form, then all redundancy based on functional dependency has been removed. Functional dependency, we have already done this, we dedicated an entire video to functional dependency. So all redundancy based on functional dependency. So if you have a functional dependency and that is causing any redundancy there, then it has to be removed, although other types of redundancy may still exist. For instance, we mentioned about the multi-attribute dependency, and also there are joint dependencies. We'll talk about that later. So 3NF does not deal satisfactorily with the case of a relation with overlapping candidate keys. So the question of BoyceCodd normal form usually arises when you have candidate keys. Candidate keys means set key or set of keys that could have been the primary key, and there is something overlapping between them. It means one attribute is common between two potential set of candidate keys. So when that is the case, the composite candidate keys with at least one common attribute, then that can result in a functional dependency causing redundancy in the data. Technically speaking, a relational schema R is in BoyceCodd normal form if and only if for every one of its dependencies X implies Y, at least one of the following conditions hold. So if you have X implies Y, either it's a trivial functional dependency, which means that Y is a subset of X, or X is a candidate key for a schema R. So for any X to be determined Y, either Y has to be a subset of X or X has to be a candidate key. Let's look at this example to understand what is going on. So in this example, you can see that we have the student ID and then the major that student is doing. So for instance, if you are in GIK, you could be doing computer science or EE or mechanical, and your advisor is here, and then your GPA is here. So what's the problem? You have the student ID and the major. So a student can be in two majors as well. Therefore the student ID alone is not enough, because you can see that it can have repeating values. So the student ID and the major combined, they form the primary key. Now if I look at it, major is dependent on the GPA is dependent on the student ID and the major, so I have a different GPA. If I am student 1, 2, 3, I have a different GPA for physics and I have a different GPA for music. So nothing is wrong, there is no question of partial dependency, it's a full functional dependency. And then if I look at advisor here, and then for my major in physics I have Stephen Hawking as my advisor, and for music I have this gentleman as my advisor. So what could possibly go wrong? Why is there a problem? The problem here is that if you look at this diagram, this dependency diagram, you can see that the student ID and the major is determining the advisor and the GPA, but there's also another dependency here, and that dependency is that the advisor is linked to the major. So for instance, if you have me as an advisor and I am a faculty member of CS, then this is becoming a redundant information. Look at it here. You have from this row, so from this row you can deduce that Hawking here is in the department of physics, and if I look here, then this information is repeated, and the reason being that I could have chosen, instead of having student ID and major, I could have chosen student ID and advisor, and that could have given me a unique value, assuming that you don't have the same advisor or the same name in different departments. That could have given me another unique value. And so you see that if you look here, in this case, composite candidate keys with at least one attribute in common. So it could have been SID and major, and could have been SID and advisor, and this SID here is common between the two candidate keys. That's assuming that this is unique. So in that case, you will see that there is a problem here, and this information is being repeated to me. So this is what we call as there is redundancy based on functional dependency. So based on functional dependency, the fact that I'm being told that Hawking belongs to the physics department, and I'm being told the same thing again, that Hawking belongs to the physics department, this is considered a redundancy. And if Hawking, for instance, suddenly decides to shift departments and go from, I don't know, physics to computer science, for instance, then there are multiple places then I have to make this change over here. So this is an example of a violation of the BoyceCodd normal form. It's an advanced or a more constrained form of the third normal form. And what I'm going to do is I'm going to divide it into two parts, and the first part will have the student and the advisor and GPA, and then here I have the advisor and the major. So if the student is working with Hawking and Hawking is in physics, then I know that this 4 GPA is for courses in the physics department, and this 3.3 GPA is because this gentleman here, Meller, is working in the music department. So therefore this GPA over here I can map it to the music department, and this GPA over here I can map it to the physics department. So the original table has now been divided into two tables, and now this here is in the BoyceCodd normal form. This is in 3NF, but not BoyceCodd normal form. So usually the BoyceCodd normal form is greater than 3NF. So if something is in BoyceCodd normal form, it means it is automatically in 3NF. But if something is in 3NF, it may or may not be in the BoyceCodd normal form, depending on whether this kind of situation exists or not. So that's the first advanced normal form that we have studied, the BoyceCodd normal form. And then moving on, we have another type of dependency issue, which is the multi attribute dependency. And to resolve that, we use the fourth normal form. So the fourth normal form eliminates independent many-to-one relationship between columns. So to be in the fourth normal form, you have to first be in the BoyceCodd normal form, and a given relation may not contain more than one multi-valued attribute. So for instance, I have a database about the movies, and so I have the movies over here. I have the city in which they are showing, and then I have the genre of that movie. So in this case, to make it a unique, then I have to underline movie, I have to underline this, and I have to underline this. So the three attributes combined will form the primary key. So because all the attributes are part of the primary key, there is no non-prime attribute left. You remember we discussed about prime and non-prime attributes? There is no non-prime attribute left. Since there is no non-prime attributes, it means you cannot have transitive dependency. It means you cannot have a functional dependency that will result in redundancy. So automatically this is in BoyceCodd normal form, because there is no non-prime attribute. All the attributes are part of the primary key. So there is no attribute that is not part of the primary key, such that we can say, okay, this violates this normal form, that normal form. So this automatically going to be in the second, third and BoyceCodd normal form. पार्शियल डिपेंडेंसी का भी कोई इशू नहीं है इसमें, क्योंकि कोई नॉन की एट्रीब्यूट है ही नहीं यहाँ पे. So in this case, what is the problem? The problem here is that when I have a movie called Hard Code that's showing in Los Angeles and that's showing in New York, and it's a comedy movie. So the fact that Hard Code is a comedy movie, this here is this information. Let me put it like this so that you don't confuse it with this primary key value. So that is the problem. Just because there were two cities, this information is being repeated, and technically we know that this is wrong because you're repeating the information. But if you look at the rules, then none of the rules are violated, since there is no non-prime attribute here. So it's in second normal form, it's in third normal form, it's in the BoyceCodd normal form. So the scheme here is the movie name, this, and the primary key is the combination of all the three. So all columns are part of the only candidate key, hence it's in the BoyceCodd normal form. But many movies can have the same genre, and many cities can have the same movie. So this is violating the fourth normal form. It says a given relation may not contain more than one multi-valued attribute. So this is a multi-valued attribute, right? So it does not mean that it's the same attribute and multiple values like the phone numbers when we transform from the unnormalized to the first normal form. That's not what we're talking about. We're talking about the combination of this and this. For Los Angeles, Hard Code and comedy is the same thing. For New York, Hard Code and comedy is the same thing. So for this attribute, the other two are having repeated values. So in that case, the fourth normal form is violated. So this is called a violation due to a repeating multi-valued attributes. And the way to do is that we are going to have to split the data into movies and screening cities and movies and the genre. So we are going to split this data, and then we are going to solve this problem. And the final form of normalization that we will study in this course is called the fifth normal form. So the fifth normal form is satisfied when all tables are broken into as many tables as possible in order to avoid redundancy. once it is in the fifth normal form, it cannot be broken into further into smaller relations without changing the facts or the meaning. So if in a schema all the tables are broken down to their lowest possible value, when I say the lowest possible value, I can break everything down to just one column. Why can't I do that? And no, you cannot do that, because if you do that, you will lose information. How, we see in the next slide. But to be in the fifth normal form, you must be in the fourth normal form, and you must not have any join dependency. So to understand what all this means, let me take you back again to that very important video about functional dependency. I keep referring to that video. You have to go and watch that again carefully to understand what we're doing here. So if you remember, we had this example when we were talking about the spurious tuples. When we talk about the, I don't know the spelling of that, tuples. I don't think there are. So when we are talking about the spurious tuples, we said that we had this table. So this was basically an employee and project and location table. So this is the social security number of the employee. This is the project number, the hours that employee worked on this project, the name of the employee, the name of the project or the product, and the location of that project or product. So this is a table. If we divide this table, we looked at this example previously in a lot more detail. If you divide this into this table into two parts, so the first one is, since this thing is being repeated, you have the employee name. John Smith is working on product X and John Smith is working on product Y, and so you separate that, the employee name and the project location, and then you have the social security number, the project, and all this here. If you divide this into two, we saw in that example that once you recombine that using the natural join, so if you recombine using a natural join, all these values are spurious tuples. So all of them here, these asterisks, they are spurious tuples. It means they did not exist in the original table. They have been created because of the join and did not exist in the original table. So let's look at this here. This ID 1 through 9, number 1, 32.5, X Bellier, and English Joyce. This never existed over here. There's only one value with 32.5. That's John Smith working on product X. So where did this come from? How does Joyce English work on product X for 32.5 hours? It does not exist in this table. So this is a result of the joining between these two tables. So let's go back to the definition. Just once we have recalled this problem with the spurious tuples, let's go back to the original definition. So when all tables are broken into as many tables as possible, so this breaking of table is not possible. Why? Because when you rejoin it, you will create or you will destroy information. So this is not possible. However, for whatever is possible, if you break the tables into as many small tables as possible, so once in the fifth normal form, it cannot be broken any further without changing the meaning or the facts. So if you break every table to the smallest possible value such that you can still recombine it and get the original table, you are in the fifth normal form. It means theoretically, that is the maximum you could go, because you cannot break any further. If you break any further, you are going to lose information when recombining to get the original information. So that is the fifth normal form. It's very rarely encountered, but it is there, and in some cases it may even be used, even though it's more of a problem that is encountered in theory. You'll see that in textbooks, but in practice it is rarely encountered, but it's not something that cannot be encountered. So that's it with the fifth normal form. So we have seen three new normal form, advanced normal forms, and those are the BoyceCodd normal form, the fourth and the fifth. And the way to deal with this is that if you can break the table into smaller tables such that you will be able to recover the original data, then do so. Otherwise, don't do it. So अगर टेबल मज़ीद ब्रेक हो सकती है इस तरह से कि आप चीज़ वापस रिकन्स्ट्रक्ट कर सकेंगे, तो फिर ब्रेक कर दें. नहीं कर सकते तो फिर जैसे टेबल है वैसे ही रहने दें. So just to look at the summary, why we did the normalization. A schema is an unnormalized form. In the unnormalized form, suffer from multiple problems: the problem of insertion, deletion, updation, redundancy, and inconsistency. And if we look at the normal forms, then the first normal form means removing the redundancy and the repeating groups. The second normal form is removing the partial dependency. The third normal form is removing the transitive dependency. The BoyceCodd normal form is remove redundancy due to functional dependency, and the fourth normal form is removing the multi-value dependency, and the fifth normal form is removing the join dependency. It's also sometimes called as the projection join. This is not project, this is projection join normal form, or PJNF. So for more practical cases, the third normal form or maximum the BoyceCodd normal form will be enough. The fourth and the fifth are rarely encountered, but that's not the limit. In theory, there can be also a sixth or a higher normal form, even higher than the fifth normal form, but it's mostly based on hypothetical scenarios, hypothetical assumptions, and it is mostly of academic interest only. It's you don't even see it, so you don't need to go into that. But in theory, there are normal forms that are higher than the fifth normal form, so you should know it. But that's all about what you need to know about them, that they do exist, but they're mostly theoretical in nature, and we're not interested in them in this course. So with that, I hope the normalization is clear. And in the next video, we'll look at certain examples, particularly for the BoyceCodd fourth and fifth, to make it even more clear, and to give you a flavor of how you will encounter them in the real world and how you have to deal with that. If you have any questions, you can ask me either in the comments on the Microsoft team or during our question answer session. So that's it for this video. Thank you very much.